Right, now let's try to find the velocity of the combined object after the collision. To find the velocity of the combination after the collision, we can apply the law. There is a law which is known as the law of conservation of linear momentum. What is the law here? What is the law that we are going to apply for the Roman number 2? According to the law of conservation of linear momentum. You should write it, right? You must write this sentence, otherwise marks will not be given. According to the law of conservation. According to the law of conservation of linear momentum. According to the law of conservation of linear momentum, right? That law tells us there's a small error here. Right? This is 20, please correct it. This is 27.2. 27.2. So this is 507.2. Please correct the mistake, right? The calculation, this is 27.2. So it should be 507.2. Please check it. Right. According to the law of conservation of linear momentum, right? It tells us the total linear momentum just before the collision. Just before the collision. The total linear momentum just before the collision equals the total linear momentum just after the collision. Just after the collision. So what is the law of conservation of linear momentum there? So it has been found by experiments that the total linear momentum just before the collision equals to the total linear momentum just after the collision. Linear momentum of a moving object is the product mass into velocity. What is linear momentum there? The linear momentum of a moving object is the product, its mass into its velocity, right? So linear momentum of the first object is the product m into u1. Object is moving into the right hand side. Therefore, direction of the linear momentum is also into the right hand side. Linear momentum is a vector. It has a direction. The direction of the linear momentum is the direction of its velocity. So velocity of the first object is in right hand side. Therefore, the linear momentum of the first object is also into the right hand side. Plus linear momentum of the second object m2, its velocity is in right hand side u2. So let's mark the direction like this. After the collision, we don't have two objects, they are combined together. We have a single object of mass m1 plus m2. That's a single object of mass m1 plus m2. It's moving with the velocity of v. Velocity v is into right hand side, so I have marked it like this. M1 is 0.6, velocity is u1 40. M2 is 3.4, velocity is 4. Then M1 is 0.6, M2 is 3.4, velocity is v. Check. 6 times 0, 0, 6 times 4, 24. 1 decimal point should be removed, so it is 24. Plus 4 times 4, 16. You have removed 1 decimal point. 4 times 3, 12 plus 1, 13. Here, 0.6 plus 3.4, that is 4.0. 4.0. Check. So we should add 24 and 13.6. Then we will get 37.6. 37.6. I'll erase and write it here. Uh, 24 plus 33.6, that is 37.6. 37.6 equals 4 times V. 4 times V. If you take 4 to this side, 37.6 over 4 equals V. You must write the final answer in this format. V equals something. That's how you would write the answer. And you must clearly indicate the unit, meter per second. You should write V equals something and you must clearly indicate the unit. So if you divide 37.6 by 4, you get the answer as 9.4. What's the answer here? You will get the final answer as 9.4 meter per second. 9.4 meter per second. Who got this answer? Who got this answer? Isune, Ishane, Hanarume, Yashodhara, Shifa, Shafne, Umesha. Very good. Shall we go to the next part of the question? The next part of the question asks us to find the total kinetic energy of the system after the collision. Am I right? Total kinetic energy of the system after the collision. Right. Please get a screenshot. If you didn't write any of these things, please get a screenshot. I'm going to erase. Right. Let's try to find the total kinetic energy of the system after the collision. What are we going to find here? We are going to find the total kinetic energy of the system after the collision. After the collision. So after the collision, we don't have two objects. We have only one object, a block with a bullet. Bullet is inside the block. So mass of the object is m1 plus m2. Its velocity is v, and we have to get the square of this velocity. You are trying to find the total kinetic energy of the system after the collision. Here, please give a try. Right, many students have sent me the answers. Good. Right. mass of the combined object M1 0.6, M2 3.4, velocity 9.4 and square of that. So this is half. 0.6 plus 3.4 means 4.0. And what is 9.4 square? What is 9.4 square?
88.36.
88.36. 88.36. 4 divided by 2 is 2 into 88.36. Let's multiply this by 2. 2 times 6, 12. 1 remaining. 2 times 3, 6. Plus 1, 7. 2 times 8, 16. 1 remaining. 2 times 8, 16 plus 1, 17. So 176.72 joules. Please check whether you have obtained this answer. 176.2 joules. 176.72 joules. Check. Shifa, Fasla, Loshan, Umesha, Ishane. Any other students? Tisuni, Yashodhara. Any other student who got this answer? Okay. Very good. Now they ask why there is a difference between the initial total kinetic energy and the final total kinetic energy. The question asks why there is a difference between the initial total kinetic energy and the final total kinetic energy. What is the kinetic energy before the collision? What's the total kinetic energy before the collision? Total kinetic energy before the collision was 507.2 joules. Find the initial kinetic energy is 507.2 joules. After the collision, you see the 40 meter per second velocity is highly reduced. But the reason is during the collision, you see what will happen? Let's say if I collide my hands, what will happen? Sound energy is generated. If you hit a nail by using a hammer, not only the sound energy but heat energy is also generated. So during a collision, sound energy and heat energy and some other forms of energy are generated. But actually, energy is not generated. The kinetic energy is converted into sound and heat energy. So huge amount of initial kinetic energy is converted into the other forms of energy such as sound energy and heat energy. So as kinetic energy is converted into the other forms of energy, final kinetic energy is less than the initial total kinetic energy. Got it? Right. So please write, put the question number and write. During a collision, comma, a huge amount of kinetic energy. During a collision, comma, a huge amount of kinetic energy is converted into the, during a collision, a huge amount of kinetic energy is converted into the other forms of energy. Other forms of energy, comma, is converted into the other forms of energy, comma, such as sound energy and heat energy. Such as sound energy and heat energy. during a collision, comma, a huge amount of kinetic energy is converted into the other forms of energy, comma, such as sound energy and heat energy. Full stop. Therefore, the final kinetic energy is smaller. Therefore, the final kinetic energy is smaller than the initial kinetic energy. Therefore, the final kinetic energy is smaller than the initial kinetic energy. Got it? So if you want to repeat, please tell me. Right, now I'm going to explain a new theory section. Look at board here. So due to the collision, what has happened here? Due to this collision, kinetic energy is reduced. Why? Because kinetic energy is converted into the other forms of energy. So if kinetic energy is converted into the other forms of energy, if the kinetic energy is reduced due to a collision, such a collision is said to be inelastic collision. Right? What's it? If kinetic energy is reduced due to a collision, that collision is said to be an inelastic collision. And look at board, please don't write anything. And the other thing, here it is fired towards a wood block. Here it is fired towards a wood block. Right? Let's say this is fired towards a tree. Then what will happen? There is a tree. Like this. I have drawn a very beautiful tree. Let's say a bullet is fired towards this tree with a velocity of u meter per second. Then this tree collides with the tree, bullet gets embedded in the tree, and bullet and the tree starts to move as a single object in the sky. Is it possible or impossible? Listen carefully, what's the story? A bullet fired with a larger velocity, it hits the tree, the bullet gets embedded in the stem of the tree. After that, the bullet and the tree start to move as a single object in the sky. Is it possible or impossible? It is impossible. So bullet gets embedded in the tree and velocity of the bullet will be 0. It will come to rest inside the stem of the tree. Then what is the final kinetic energy of the system then? What is the final kinetic energy of the system? Half m1 mass of the bullet, m2 mass of the tree into the square of the velocity. Velocity is 0. So final total kinetic energy is equal half into total mass into 0 square. 0 into anything is 0. So after the collision, what is the total kinetic energy here? What is the total kinetic energy after the collision? 0. So
0.
such a collision is said to be perfect inelastic collision. Perfect inelastic collision. Right? The third one is said to be elastic collision. What's the third kind of the collision here? Elastic collision. So please write the next subheading, the kinds of collision. Please write the next subheading, the kinds of collision. The kinds of collision. The kinds of collision. Please write the next subheading, the kinds of collision. Under that, please write, there are 3 different collisions in the universe. Under that, please write there are three different collisions in the universe. There are three different collisions in the universe. Subheading is the kinds of collision. Under that, please write there are three different collisions in the universe. Then put 1, 2, 3 and write inelastic collision, perfect elastic collisions, and third one, elastic collisions. Please write these three here. There are three different collisions in the universe. So please write them all quick. Some student had already paid for the class, so I'm going to post them soon, right? I'll send it to you soon by post. Or I can arrange a courier service. Right, then please write your first subheading. It's better to write put number 1 and write the first subheading. Inelastic collisions. Inelastic collisions. Inelastic collisions. Inelastic collisions. Under that, write the description. If the kinetic energy is reduced, if the kinetic energy is reduced during a collision, if the kinetic energy is reduced during a collision, if the kinetic energy is reduced during a collision, you write put number 1 and write the subheading inelastic collision. Under that, write the description. If the kinetic energy is reduced during a collision, full stop, during a collision, comma, during a collision, that collision is said to be an inelastic collision. If kinetic energy is reduced during a collision, comma, that collision is said to be an inelastic collision. An inelastic collision. An inelastic collision. Okay. Continue. Majority of the collisions in the universe, full stop and continue. Majority of the collisions in the universe are inelastic. Majority of the collisions in the universe are inelastic. Majority of the collisions in the universe are inelastic. Then write the next subheading, put number 2 and write the next subheading. Perfect inelastic collisions. Perfect inelastic collisions. Perfect inelastic collisions. Right. Under that, please write. If the kinetic energy is completely wasted, if the kinetic energy is completely wasted, and if the kinetic energy is completely wasted and objects, all the objects come to rest. If the kinetic energy is completely wasted and all the objects come to rest, all the objects come to rest. If kinetic energy is completely wasted and all the objects come to rest during a collision, during a collision, comma, during a collision, comma, that collision is said to be a perfect inelastic collision. If kinetic energy is completely wasted and all the objects come to rest during a collision, comma, that collision is said to be a perfect inelastic collision. Said to be a perfect inelastic collision. Leave a line and write examples. Number one. Examples. Number one. When a bullet is fired towards a tree, comma, it hits the tree. When a bullet is fired towards a tree, comma, it hits the tree and comes to rest inside the stem of the tree. When a bullet is fired towards a tree, it hits the tree and comes to rest in the stem of the tree. In the stem of the tree. Draw this figure. Quick. In the exam, if they ask you to write examples, no need to draw figures, right? But here I have drawn a figure to explain. What is example number 2? Example number 2. Let's say, don't draw the figure, please don't draw the figure. Let's say you get a wet clay ball. A wet clay ball. If you throw a wet clay ball towards a stationary wall, what will happen? The wet clay ball hits on the wall, it pastes on the wall and comes to rest. So finally, the wall and the wet clay ball both are at rest. So kinetic energy completely wasted. There is no more kinetic energy and objects are at rest. So it is a perfect inelastic collision. So put number 2 and write. When a wet clay ball, is thrown towards a wall, it collide with the wall and comes to rest on the wall on the wall. It collides with the wall and comes to rest on the wall. Please draw this figure. Draw this figure quick. Okay, I think you have drawn the figure. So we have completed two of the collisions in the universe. I'm going to describe about the third kind of collisions in the universe. So please write, put number 3 and write the third subheading, elastic collision. Elastic collisions. Elastic collisions. Right. Elastic collisions mean there is no waste in kinetic energy. If several objects had certain amount of kinetic energy before a collision, after the collision, the same total kinetic energy will be there with the objects. So there is no change in the total kinetic energy during a collision. Then that collision is said to be an elastic collision. Clear? So put number 3 and write the third subheading, elastic collisions. Elastic collisions. Under that, please write, if the kinetic energy is not wasted, if the kinetic energy is not wasted during a collision, if kinetic energy is not wasted during a collision, comma, such a collision is said to be an elastic collision if kinetic energy is not wasted during a collision. Such a collision is said to be an elastic collision if kinetic energy is not wasted during a collision, such a collision is said to be an elastic collision. Right. So we are going to do some examples for elastic collisions. Before that, please write, put a star point and write, the following equation can be applied for an elastic collision. The following equation can only be applied for an elastic collision. Please re-edit and write, slightly edit and write. The following equation can only be applied for an elastic collision. The following equation can only be applied for an elastic collision. What's the equation there? What's the equation? Look at board. Total KE, look at board, please don't write. total KE before the collision. Total KE before the collision equals to the total KE after the collision. So this can only be applied for an elastic collision. Please write this equation and draw a box around it. Highlight it. Very important. Very important. Complete.
Excuse me, sir.
Any doubt?
Excuse me, sir. Can't we write this equation as total initial kinetic energy and total final kinetic energy?
Yeah, you can write. You can write this as initial total kinetic energy equals final total kinetic energy. Yes, definitely.
Thank you, sir.
Yes. If you have doubts, please ask. I really appreciate if you ask doubts. Let's discuss a question for this. Let's discuss a question related to the elastic collisions. So please write example number 1. Example number 1. Two trolleys travel along the same path. Two trolleys travel along the same path into the same direction. Two trolleys travel along the same path into the same direction, and two trolleys travel along the same path into the same direction, and they collide as an elastic collision. They collide as an elastic collision as shown in the following figure. They collide as an elastic collision as shown in the following figure. Look at board. Two trolleys travel along the same path into the same direction, and they collide. It is said that the collision is elastic. It is said that the collision is elastic. It means kinetic energy is not wasted. Kinetic energy is not wasted. Right. After the collision, look at board. After the collision, they will move with two different velocities. Draw the figure here. Draw the figure. After that, I'll give you the questions. So after the collision, they move as two different objects. The point here that you would remember is this is an elastic collision. This is what you want to remember. Yeah, I'll repeat. Two trolleys travel along the same smooth horizontal path, and they collide as an elastic collision as shown in the following figure. Two trolleys travel along the same path into the same direction, and they collide as an elastic collision as shown in the following figure. Still, if you won't repeat anything, please ask. Sometimes you will not be able to write the notes. If so, please ask. Mass of this one is 3 kilogram. Mass of this one is 1 kilogram. So this is the situation just before the collision. Mass of the first trolley 3 kilogram. Mass of the second trolley 1 kilogram. And this is the situation just after the collision. Just after the collision. I'll mark the velocities also. I'll mark the velocities also. Velocity of the first trolley before the collision. Let's say 4 meters per second. Velocity of the second trolley before the collision, let's say 2 meters per second. Velocity of the first trolley after the collision, let's say V1 meter per second. Velocity of second trolley after the collision is V2 meter per second. Please draw the figure. Please mark all the given data. And if you have any doubt, please ask. I can help you. Start. I have a student with a completely different name saying easy class. Who is that? Who is easy class? Please send me a message. It's impossible for a man to have such a name, easy class. Suddenly he left the class. Good. Right, please write, find the velocity of the trolleys. Please write the question, find the velocity of the trolleys just after the collision. Find the velocity of the trolleys just after the collision. Find the velocities of the trolleys just after the collision. Find the velocities of the trolleys just after the collision. Right. Here, both velocities are not given. The velocities of both trolleys after the collision not given. That's the case. So we have to apply this equation, and we can apply this equation because it is said that the collision is elastic. So please write, as the collision is elastic, as the collision is elastic, as the collision is elastic, comma, the following equation can be applied. As the collision is elastic, comma, the following equation can be applied. As the collision is elastic, comma, the following equation can be applied. So write the equation: total kinetic energy before the collision equals total kinetic energy after the collision. Total kinetic energy before the collision equals total kinetic energy after the collision. Write it. Right. The total kinetic energy before the collision is kinetic energy of the first trolley is half m1 u1 square. Kinetic energy of the second trolley half m2 u2 square. So summation of these two is the total kinetic energy before the collision. So total kinetic energy after the collision means half m1 v1 square. V1 is the velocity of the first trolley after the collision, plus half m2 v2 square. V2 is the velocity of the second trolley after the collision. So please write it. So it is half m1 is 3 kilogram. M1 is 3 kilogram. U1 is 4. Square of 4. Half M2 is 1 kilogram. U2 is 2 meter per second. 2 meter per second. Equals half M1 is 3 kilogram. V1, we don't know the value of V1. Plus half M2 is 1 and we don't know the value of V2. Now you should understand that all the half terms, this half, this half, this and this, all the half terms can be cancelled out. Check whether you can understand it here. All the half terms can be cancelled out. Check. All the half terms can be cancelled out. So what are the remaining numbers? What are the remaining numbers? 3 into square of 4, that is 16, plus 1 into square of 2, that is 4, equals 3 and v1 square, 3v1 square, plus it is just 1v2 square, 1v2 square. 3 times 16, 3 times 6, 18, 1 remaining, 3 times 1, 3 plus 1, 4, plus 1 into 4 is 4, equals 3v1 square, 1v2 means v2, 1 into v2 square means v2 square. 48 plus 4 is 52 equals 3v1 square plus v2 square. Let me take this as my first equation. This is my first equation. Please complete it, dear. Let's complete this. So this is our 2023 AL online class. The heading. Write it. Yeah, actually, even in my 21 batch and 22 batch, I have a lot of students from Gampola area. Gampola, Navalapiti area, I have a lot of students. Gampola, Navalapiti, Akkarepattu, Jaffna, Trinco, yeah, many students are there because I think because of the English language, the students are joining to my class. Even some students from Matale. Right. See, this is an elastic collision. Yes, this is an elastic collision. So therefore, kinetic energy is not wasted. So we can apply total kinetic energy before the collision equals total kinetic energy after the collision, or total initial kinetic energy equals total final kinetic energy. Whatever the collision, whether a collision is elastic or inelastic, we can apply the law of conservation of linear momentum. Whether a collision is elastic or not elastic, for both elastic and inelastic collisions, we can apply the law of conservation of linear momentum. So please write, let us apply the law of conservation of linear momentum. Let us apply the law of conservation of linear momentum. Let us apply the law of conservation of linear momentum. Let us apply the law of conservation of linear momentum. Let us apply the law of conservation of linear momentum. Come on, you align and write this equation. Total Lm before the collision. Lm means linear momentum. Total linear momentum before the collision. Total linear momentum before the collision equals total linear momentum after the collision. Total linear momentum before the collision equals total linear momentum after the collision. Please write. This is known as the law of conservation of linear momentum. Right. Total linear momentum. Linear momentum is the product mass into velocity. So the mass of the first object m1 into its velocity u1 before the collision. Objects are moving into the right hand side, so I'll mark the direction into the right hand side. If an object is moving to a certain direction, its linear momentum is also into the same direction. Linear momentum is a vector. It has a direction. Its direction is equal to the direction of the velocity. Right. The linear momentum of the second object before the collision is m2 into u2. It is also into the same direction. Linear momentum of the first object after the collision is m1 into v1. Linear momentum of the second object after the collision is m2 into v2. Got it? Right. Equation mark. Equation mark. M1 is 3 kilogram. U1 is 4 plus M2 is 1 kilogram. U2 is 2. U2 is 2. M1 is 3 kilogram. V1 is V1. We don't know it. M2 is 1 kilogram. Velocity is V2. 3 times 4 is 12 plus 1 into 2 is 2 equals 3V1 plus V2. 12 plus 2 is 14 equals 3V1 plus V2. This is our second equation, not the third. Second equation. Mark it. Second equation. Second equation. Right. Now you are going to be very sad. You are going to be very sad. Because I'm going to give you a homework. Here we have 3V1, only V2. Here we have V1 square, V2 square. Therefore, the terms are completely different. V1, V2, here square terms are there. So at home, try to solve the two equations, 1 and 2 equations. Try to find V1 and V2. Get a photo and send to my WhatsApp. Do not send your answers to the group, dear. It's not good because it will be a disturb for the other students. Because then the students can copy answers from each other. So I don't want to do it. So therefore, if you get an answer, please send to my WhatsApp as a personal message. So I can check, I can mark and return your answers. Right? So what's the homework? What's the homework? Solve this 1 and 2 equations and send me your answers. Okay?